Okay, today we'll begin your model 4 that is totally devoted to the sampling and quantization concept. Briefly, we know about this, what we mean by sampling and quantization, and this we studied bit in detail as a part of communication related subjects like analog and digital communication. So let us begin with this one, what we mean by sampling and why it is required here. Sampling, the name itself, it will indicate that it is the process to convert an analog signal into a digital signal. So the literal meaning of this sampling is to cut a continuously varying analog signal into a discrete time or digital signal. So simply by doing the sampling, we cannot get our digital signal. So after cutting the analog signal, a continuously varying analog signal will get discrete values, and those values should be quantized properly. Then we are able to get the digital signal. So everything depends on how we are going to do the sampling process and quantization procedure. In case of sampling procedure, the sampling frequency, what you are keeping, that is going to tell the reliable operation of sampling. And in quantization process, the quantization step size is going to decide how well we are going to do this conversion from analog to digital. So these two things, the sampling rate or frequency and quantization step, are the two key factors in converting your analog to digital signal. Because later we have to recover our signal back. So why actually we need to convert analog signal to digital signal? So the main idea behind is this. So most of the signals in the real world are going to be analog signal. Now, for example, what we are discussing now is speech signal you are listening all the way from the college to your residential or domestic places, which will be converted to digital modulation technique will be used. Then you will be getting your analog signal back there. But what I am talking or speech signal, it is an analog signal. Similarly, the temperature, it is an analog signal. Video, what you are watching is analog signal. Sometimes if you want to mix video, if somebody is singing, if you want to mix that one with the soundtrack, background sound noise, background music, something like that, all such things are going to be analog only. So most of the things which are appearing in the real world are going to be analog signals only. So therefore, we need to convert such signals into digital signals. So why this conversion is actually required? So we can quote many reasons here. Already we know about that. One is the flexibility of the technology provided by the digital communication technology compared to analog communication technology is very much feasible one. In terms of the bandwidth it will provide, in terms of the hardware or circuits we can design is going to be more easier one compared to analog. In terms of the modulation techniques that we are using as a part of digital compared to analog is going to be much flexible and optimized and more efficient. Even the cost, the compactness are more liking factors in case of digital as far as analog is concerned compared to analog. So many advantages are there. So main advantage is this bandwidth. and sensitivity to the noise. Our digital system is very much less sensitive to the noise. It will not, it is prone to the noise, you can say, as compared to the analog communication system. So because of all those many reasons we can quote, important reasons, we will go for converting analog to digital signals conversion. So these are the different reasons we can discuss here. So digital systems are less sensitive to noise. We have discussed in detail in the third module the impact of noise in analog communication systems. In detail, we discussed with respect to DSB, AM, and FM. Even in case of super data and receivers or stereo multiplexing, we have taken up the cases separately, how to deal with these different kinds of noises and their impacts in transmission of these analog signals, and how we go on modifying the block diagrams itself in order to deal with each of the noises in separate cases of AM and FM. So compared to all those issues that we have discussed about the noise impact in the analog communication, to the maximum extent are resolved in case of digital systems. That's why we can say it is a less sensitive to the noise. Inherent, it is an inherent property of digital systems. So this is a very important property, so that our whole communication process, if it will become immune to the noise. So other than that, what is required? Even you like to go for paying more for that. So second reason is a digital systems, which will allow easier multiplexing of a video with the soundtrack on same channel. So this is very important, guys. The digital system allows to make use of a single communication channel to send more than one information at a time without losing the information. Like if you want to mix up and send the video and soundtrack at a time, that is possible with the same bandwidth. That is another genuine reason we can quote. That's how I can tell it is going to provide with a large bandwidth, so that it can accommodate more number of informations, different types of data we can send. Transmission scheme is independent of source. So that's another important property. For example, suppose if I am transmitting the voice signal at 10 kbps, same can also be used to transmit my computer data at the same rate, same data rate, 10 kbps without overlapping. That's why he is telling that independent of the source of data. The same data rate or channel capacity you can use to transmit different types of information at a time without overlapping. That is a very important property of the digital systems. So these two things, guys, you have to remember. One, it is allowing you to send more type of information at a time, and at the same channel capacity it is allowing, means same bandwidth. So this is very important. So the next one is the digital circuits are easier to handle, less prone to vibration and temperatures, and most of the time you can feel that digital circuits are easy to design, implement, use. Most of the time we have felt that one. And obviously they are less prone to vibration and temperature. Hardware, therefore the hardware design will become easier. Many times we felt that we are feeling very easy to design combinational circuit, sequential circuit designs compared to the analog circuits. So the main reason why we are feeling it very easy, because in case of digital design, all the way we'll have to depend on the basic gates. Ones and zeros are there. We are not talking about any other value other than 1 and 0. That's why it is very easy. Even you can look at the thread table or KMAP or whatever the synchronous logics. Everything will depend just on the two states, 1 or 0. But whereas in the design of the hardware, as far as the analog is concerned, the signal is continuously varying, we'll have to consider a lot of factors there. So this is another aspect that why we are feeling the digital hardware design is going to be much flexible compared to the analog hardware design. So the next reason what we can quote for why we go for digitizing the analog sources is specification of complex international standards becomes easier. We can easily adopt any kind of international, even though let it be complex standards, it will become much easier to adopt here. So that is, hello, okay. That is the another reason that you can quote for why you are going for digitizing the analog sources. And the techniques like multiplexing, equalizing, and many other things, digital transmit technologies can be easily adopted in case of digital systems compared to the analog systems. So like that, we can enlist the comparison between the differences between the analog and digital communication systems like this. The first one, bandwidth is more in case of digital system compared to analog. Error correction and detection is possible compared to analog. Immune to noise very important. Your digital system is more immune to noise compared to the analog. System complexity is very much reduced. Quality of instruction is very good in case of digital system. System cost is very much reduced in case of digital system. Synchronization, if it is required between transmitter receiver, is very well versed in case of digital system. Security of your data is very much reasonable in case of digital system. Flexibility, liability is very much well advanced in case of digital system compared to analog system. Power required is very much reduced because once if you reduce the bandwidth, so you can provide a large bandwidth to transmit as many number of data as possible. The corresponding hardware design will be very much reduced, and then the power requirement will also be reduced. Implementation will become easier, and programming is possible compared to the analog system. So these are the main important reasons that you can formulate here in the form of table here. So two questions we can expect here. So why we are going for digitizing the analog sources? So these are the reasons we have to discuss in our own words. Don't put the stars or table here. So table I'm just showing here for the convenience of discussion. So these are the key points you have to keep in mind and have to explain. Either of the question if you go to comparison between analog or digital communication system, or you get the question like why digitizing the analog sources, you have to keep these points in mind and discuss in the own words. So don't put the table at any cost. Next one, we can start with the sampling process here. The sampling theorem states that any continuous time signal, that you remember here, any continuous time signal means its amplitude is instantaneously varying with respect to time, can be completely represented in its samples, in terms of its samples, having a specific width and height in terms of samples, having its own quantization levels, which are going to vary as per the instantaneous variation of the analog signal. And recovered back, all those samples can be recovered back. If the sampling frequency, this is a very important condition, if the sampling frequency is greater than or equal to 2 times the highest frequency component of the baseband signal. This is very important. Where W is the highest frequency in the baseband continuous time signal. This condition is called Nyquist condition or a sampling process. Nyquist condition or Nyquist rate of the sampling process. So one thing you remember, the sampling frequency should be greater than or equal to 2W. W is the highest frequency component of your baseband signal. So let us see its mathematical discussion. We will continue with the instantaneous sampling here, a low frequency kind of sampling here. So let us consider an arbitrary signal g of t as it has been shown in the block diagram here. Arbitrary means one randomly varying analog signal. Randomly having the shape, that kind of signal is called arbitrary signal. Having the finite energy as shown in the figure, we will consider here. So this one we want to convert it into digital using this sampling or instantaneous sampling process. So for that purpose, let us consider that this g of t is sampled at every ts seconds. At every ts seconds, we are going to chop it. Instantaneously, it will be chopped, our analog signal g of t, at every ts seconds, which leads to the sequence of infinite samples, and those infinite samples are spaced at every ts seconds. Means we will get g of n ts. N will be any integer. So this chopping will be done at fs equal to 1 by ts. So the sequence of impulses will be as shown in figure B here. So we are going to chop our g of t with the help of these impulses. Then we are going to get our gn of ts. Okay. Who is playing this music? Swapnil. If this will occur, I will have to remove you. So let us consider a G2 of t denote the signal obtained by individually weighing the elements of a periodic sequence spaced ts seconds. The sampled output G2 of t is given by, we are multiplying this S dou of t, that is a periodic impulse train. A train of impulses we are going to multiply for our g of t. Means analog signal g of t is multiplied with a sequence of impulse trains, so that we will get the chops. The chopping here it is done by the impulses. So the impulses which are located at the separated by ts period are going to cut your instantaneously varying analog signal g of t at the same distance. So you call this g dou of t as equation number 1 and a periodic impulse train as equation number 2. So once you multiply g of t with this periodic impulse train, that is by equation number 2, then you will be getting g dou of t as shown in figure C. Such kind of figure you are going to get. So you can see here analog P is similar to the analog only. Only thing now your analog instantaneously varying signal will not be there. That will be replaced by these instantaneously varying impulses. Now substitute 2 in 1, what we can get? We can substitute this one, S dou of t in equation 1. You can replace S dou of t by this. So what you can get? G of t into, then S dou of t will be remaining as it is. Then using the shifting property of the impulse that we learned in signals and systems, shifting property. So G of t into dou t minus nts. If you multiply these two, what will you get? G of nts into dou t of nts will get. Again from n varying from minus plus infinity, G dou of t will get like this as equation number 3. So up to equation number 3 will be the step 1. What we did? We considered one finite energy analog signal multiplied with periodic impulse train S dou of t here, and we got gs of t, this one, by using shifting property of the impulse function. Next, for the frequency domain, g S of t equal to g of t into s dou of t is there. We have to consider this one, not this. We have to consider this the previous one, this one. We'll take the Fourier transform on both sides. G dou of f, g of t will become g of f, and s dou of t will become s dou of f in frequency domain using the Fourier transform, where s dou of f will become fs summation dou of f minus nfs. Substituting 5 in 3, so this one will substitute in equation number 4 here. So what we will get? G of f star, this one, fs summation dou of f minus nfs. From convolution property of impulse function, so we know that one. Convolution between the spectra of two signals, if you apply that property, we will get g of f minus fs. So g dou of f, we will get it as, so this one, fs summation g of f minus nfs. So equation 6 can be rewritten as if we expand this one, fs g of f plus fs summation n not equal to 0. This one is for n equal to 0. Because of the impulse located at the origin, we are getting this term. Remaining terms, we are getting the harmonics situated symmetrically on either side of the origin. Now, when you pass this equation number 7, this signal, frequency domain signal, through the low pass filter, the second all harmonics will be removed. We will get only fs g of f. Then, after taking the inverse Fourier transform, we will be getting the g of t like this. So this is the second step. From equation number 4 to 7, what we did in the frequency domain, we applied the ft on either side, applied the convolution property, then passed it through the low pass filters. Then the first term is retained, applied the inverse Fourier transform to recover back our g of t. So this is how the sampling process is going to happen. The next class we are going to discuss how we will go for over and under sampling along with some numericals. Till that, you can practice this mathematical discussion, what we have discussed. That is important to discuss specifically how over and under sampling is going to happen.